By the end of the last chapter, we had found something small, hidden, and almost impossible to believe. A handful of microscopic crystals, 4 1/3 billion years old, carrying a faint chemical signature suggesting that somewhere, briefly, liquid water may have touched Earth's surface. It was a whisper, a single contested clue, buried in the atomic structure of a mineral grain smaller than a sand particle. This episode is about what that whisper eventually became. Because sometime between 4 billion and 3.8 billion years ago, in the middle of an era still defined by bombardment and volcanism, something changed. The sky, for the first time in Earth's history, began to fall as rain. And it did not stop for a very long time. This is the story of the first ocean. To understand how an ocean could possibly form on a planet still glowing with molten rock, we need to understand what Earth's atmosphere actually looked like during this period. After the giant impact that formed the moon, and through the long, punishing chapter we covered last episode, Earth's surface was dominated by a magma ocean, a churning layer of liquid rock, in places possibly hundreds of kilometers deep. A body that hot cannot simply hold onto liquid water. Any water present in Earth's original building materials, or delivered by later impacts, would have been driven off the molten surface as vapor, joining a thick, scalding atmosphere dominated by steam and carbon dioxide, along with other volcanic gases. This is sometimes called a steam atmosphere, and it would have been genuinely strange by modern standards. Models suggest atmospheric pressure at the surface may have reached tens to hundreds of times the pressure of Earth's atmosphere today, with surface temperatures potentially exceeding several hundred degrees Celsius. Beneath that immense pressure, the sky itself would have looked nothing like the sky we know. There would have been no blue, no white clouds drifting lazily overhead. Instead, an observer, had one somehow been able to survive there, which nothing could, would have seen a dense, featureless, superheated haze, glowing faintly orange from the heat of the molten surface below, pressing down with a weight many multiples of what we feel standing at sea level today. Under those conditions, water simply could not condense into rain. It stayed locked in the sky, an enormous reservoir of vapor sitting atop an ocean of fire, waiting for something to change. What eventually changed was heat loss. As the magma ocean radiated its energy into space, and as the rate of large, heat-generating impacts gradually declined, Earth's surface slowly began to cool. This was not an overnight process, and scientists studying magma ocean solidification have proposed a range of timescales for different stages of this cooling, depending on factors like atmospheric insulation and the specific composition of the early mantle. Some models suggest an initial thin surface crust could form within a few thousand years under the right conditions, even while a deep magma ocean persisted underneath for much longer. Once a stable crust existed, atmospheric temperatures at the surface could finally begin dropping toward water's condensation point. Under the extreme pressures of this steam atmosphere, that threshold would have been far higher than the 100 degrees Celsius we associate with boiling water at sea level today. Some estimates place the relevant condensation temperatures at several hundred degrees, given the immense atmospheric pressure involved. But once that threshold was crossed, something remarkable is thought to have happened, relatively quickly on a geological timescale: rain. It is difficult to overstate how much water needed to fall in order to form the volume of ocean we know existed on early Earth. Current estimates hold that Earth's oceans today contain roughly 1.4 billion cubic kilometers of water. And much, if not all of that water, is thought to have originated in the same early atmospheric reservoir. Given the scale of that reservoir, and the physical rate at which such enormous quantities of atmospheric water vapor could plausibly condense and fall, some researchers have modeled this process as an intense, sustained downpour lasting anywhere from several thousand to a few million years, depending on the specific assumptions used about atmospheric composition and cooling rate. This was not rainfall as we understand it. It was, by any reasonable estimate, one of the most sustained and violent weather events in the planet's entire history. An atmosphere that had spent hundreds of millions of years accumulating water vapor, releasing nearly all of it in a colossal, prolonged downpour, falling onto a surface still cooling from the aftermath of planetary formation. Geologists and planetary scientists sometimes describe this kind of event, somewhat informally, as a megaflood phase of planetary history. Not a single storm, but an essentially continuous planet-wide precipitation event, punctuated by the enormous quantities of heat still being released from the cooling crust below, which would have driven powerful, continuous evaporation and recondensation cycles even as the bulk of the atmosphere's water steadily made its way toward the lowest points on the young planet's surface. As the rain fell and pooled into the planet's lowest basins, it began doing something else, almost immediately, dissolving. Rainwater falling through a carbon dioxide-rich atmosphere absorbed some of that gas, becoming mildly acidic, carbonic acid, the same weak acid found in modern carbonated water. That slightly acidic rain would have begun reacting with, and slowly dissolving, minerals in Earth's freshly formed volcanic crust the moment it touched the ground. The first ocean, in other words, was never simply pure water sitting passively on a rock. From its very first drops, it was already a chemical reaction in progress. This raises a genuinely difficult scientific question that we should address directly. Where did Earth's water actually originate? For a long time, one popular idea held that most of Earth's water arrived relatively late, delivered by a bombardment of water-rich comets after the planet had largely finished forming. This remains a serious hypothesis, and comets are unquestionably icy, water-bearing bodies. But when scientists measure the specific ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen in cometary water, the ratio in most studied comets does not match the ratio found in Earth's actual oceans particularly well. A competing and currently more widely favored explanation points instead to carbonaceous chondrites, a class of primitive water and carbon-bearing meteorites believed to represent leftover material from the outer regions of the early asteroid belt. Their deuterium to hydrogen ratios match Earth's ocean water considerably more closely than cometary ice does. This suggests that a substantial portion of Earth's water may not have been delivered in one dramatic late bombardment at all, but was instead present from the very beginning, locked within hydrated minerals inside the rocky and carbonaceous material that accreted to form Earth in the first place, described in our very first episode. Supporting this, some analyses of water trapped deep within Earth's mantle, in volcanic rock believed to originate from unusually primitive, largely unmixed regions deep inside the planet, show hydrogen isotope ratios strikingly similar to those of primitive meteorites, potentially a preserved sample of Earth's original primordial water supply. The honest scientific answer at present is probably some combination of both processes. A substantial primordial inventory of water accreted directly with Earth's original building material, possibly supplemented by later contributions from asteroids and to a lesser extent, comets. The exact proportions remain an active area of research and genuine scientific debate. Here is a question worth sitting with directly, since it goes to the heart of why Earth is habitable at all. Given how much heat this young planet was radiating, and how close it sits to the sun on a cosmic scale, why didn't this newly formed ocean simply boil away again? Back into space the way water seems to have been lost on a neighboring world? That neighboring world is Venus, and its story is instructive by contrast. Venus is thought to have formed with a substantial water inventory of its own, but sitting closer to the sun, it likely crossed a critical threshold that Earth did not, a runaway greenhouse effect, in which rising surface temperature evaporates more water into the atmosphere, which traps more heat, which evaporates still more water in an accelerating feedback loop. It is worth pausing on just how total that loss appears to have been. Venus today has essentially no water at all. Its atmosphere is overwhelmingly carbon dioxide, its surface a crushing, scorching wasteland, roughly 465 degrees Celsius, hot enough to melt lead. Whatever ocean Venus may once have had in its own early history is simply gone, evaporated skyward and then stripped away into space over the following billions of years. Once water vapor dominates the upper atmosphere of a planet like this, solar ultraviolet radiation can break those water molecules apart, freeing the light hydrogen atoms to escape into space, while heavier oxygen is left behind, often bound up in surface rock. Measurements of the ratio of deuterium to ordinary hydrogen in Venus's present-day atmosphere show a value roughly 100 times higher than Earth's. Strong evidence consistent with the idea that Venus lost an enormous quantity of hydrogen, and with it, an entire ocean's worth of water over its history. Earth, fortunately, appears to have sat on the safer side of this threshold. Part of the explanation may simply be distance from the sun. Part of it may be timing. Recall from the last episode that the young sun was itself notably dimmer than it is today, by perhaps 25 to 30%, which would have reduced the immediate risk of a runaway greenhouse during this critical window. Longer term, Earth also appears to have developed a genuine climate thermostat, the carbonate-silicate cycle, in which atmospheric carbon dioxide dissolves in rainwater, weathers surface rock, and is eventually carried to the ocean and locked away in carbonate minerals, a process that naturally intensifies as temperatures rise and slows as temperatures fall, gently stabilizing the planet's surface temperature over long timescales. Whether this feedback was already meaningfully active during the very earliest ocean's formation, or developed somewhat later, remains an area of ongoing research, but the same basic chemistry, rain reacting with rock, was already underway from the ocean's very first drops. Finally, simply holding on to an atmosphere and ocean over billions of years requires shielding from the relentless erosive pressure of the solar wind, a stream of charged particles constantly flowing outward from the sun. Earth's protection against this comes from its magnetic field, generated deep within its molten metallic core. Remarkably, some scientists have found paleomagnetic evidence, faint magnetic signatures preserved within the same ancient zircon crystals we've discussed in previous episodes, suggesting Earth may have already possessed a functioning magnetic dynamo by around 4.2 billion years ago, considerably earlier than once assumed. So what would this first ocean actually have been like, chemically, if you could somehow have stood at its shore? For a long time, the conventional assumption among scientists was that this earliest ocean must have been intensely acidic, given the carbon dioxide-rich atmosphere it was condensing from and equilibrating with. More recent modeling, however, has complicated this picture. A detailed 2017 reconstruction of seawater pH throughout Earth's history argued that continuous buffering reactions between ocean water and silicate rock on the seafloor may have kept the earliest ocean's pH closer to neutral, or only mildly acidic, rather than the strongly corrosive environment sometimes imagined in older models. What is less disputed is that this ocean was chemically active and mineral-rich from the very start. Volcanic outgassing continuously released hydrochloric acid and other volatile compounds into the atmosphere and ocean, which reacted with and slowly dissolved surrounding rock. Over time, this weathering process is thought to have released dissolved chloride, sodium, and a range of other ions into the water, the beginning of the process that would eventually give Earth's oceans their characteristic salinity. This early ocean was also almost certainly rich in dissolved iron, leached continuously from volcanic rock in a world with essentially no free atmospheric oxygen to cause that iron to rust and settle out of solution, as it does in today's oxygenated seas. That dissolved iron would remain in the ocean for well over 1 billion more years, until the arrival of oxygen-producing life fundamentally transformed ocean chemistry, a pivotal transformation we will cover in detail 2 episodes from now. The ocean's temperature during this earliest period also remains a genuinely open scientific question. Some models, accounting for the residual heat still radiating from a recently solidified crust and a CO2-thick atmosphere, suggest this first ocean may have been distinctly warm by modern standards, perhaps in a range loosely comparable to a warm bath rather than a cold sea, though estimates vary considerably depending on the specific assumptions used, and this remains an active area of ongoing modeling rather than settled fact. There is also direct mineralogical evidence supporting the idea that liquid water was present and interacting with rock remarkably early. Careful laboratory analysis of trace element concentrations within Jack Hill's zircon crystals, the same crystals discussed in our first 2 episodes, indicates that the magma from which they crystallized had likely undergone melting in the presence of water, at temperatures unusually low for molten rock, around 680 to 700 degrees Celsius, rather than the much higher temperatures expected of a completely dry anhydrous melt. This finding, independent of but consistent with the earlier oxygen isotope evidence, adds meaningful weight to the idea that a genuine hydrological cycle, evaporation, rainfall, and rock-water interaction, was already operating on Earth's surface remarkably early in its history. Let us take stock of what this chapter has covered. Sometime between roughly 4 billion and 3.8 billion years ago, a planet that had spent hundreds of millions of years as a molten, bombarded, nearly unrecognizable body finally cooled enough for its atmosphere to release the water it had been holding. Quite possibly since the very beginning of its formation. That release did not happen gently. It arrived as an extended, immense downpour, potentially lasting thousands of years or more, filling the planet's lowest basins with a chemically active, mineral-rich, and possibly near-neutral ocean. That ocean survived, rather than boiling away entirely as appears to have happened on nearby Venus, through a combination of factors still being actively researched today. A fortunate distance from a sun that was itself unusually dim during this exact window. The beginnings of a long-term climate-stabilizing feedback between rainfall and rock. And remarkably, a protective magnetic field that may have already been shielding the planet's atmosphere from space by this point. None of this yet resembled a hospitable world by our standards. The bombardment, as we covered last episode, had not fully ended. Volcanism remained widespread. The atmosphere above this new ocean was almost certainly still thick, likely still without breathable oxygen, and periodically disturbed by the largest impacts still striking the planet. But something fundamental had changed. For the first time in Earth's 400 million year existence, there was a place, vast, connected, chemically rich, and stable enough to persist, where liquid water simply sat quietly on the surface of a planet. It would not stay empty for long. That is where we go next. Thanks so much for watching till the end. If you found this video helpful, hit subscribe and share it to support the channel. See you in the next video.